Hello, myself Vishwakarma from IIPS DAV Indore, India. In this video lecture, I am going to explain numericals based on numerical differentiation, forward and backward difference operator, trapezoidal and Simpson's rule, and Gauss-Seidal method. Our first numerical is based on numerical differentiation. Here we have given with values of x and values of f at different points of x, and we have to find df by dx at x3 and d square f upon dx square at f1. First of all, we will calculate difference table. In this we have calculated delta f and del square f, which are called forward difference operator. These are obtained by subtracting present value from next value, and by using following interpolating polynomial we can calculate df upon dx and d square f upon dx square. The interpolating polynomial is f of x equal to f of x1 plus del f1 upon h into x minus x1 plus del square f1 upon factorial 2 into h square x minus x1 into x minus x2 plus r of x, where delta f1 and delta square f1 are the forward differences and r of x is the error term, which we will neglect in our solution. Now differentiating equation number 1, which we have seen, we will get df upon dx equal to del square delta f1 upon h plus delta square f1 upon factorial 2 into h square into x minus x1 plus x minus x2. From the difference table we have got forward difference operator f1 equal to 0.0097, del square f1 equal to minus 0.0001, h equal to 0.01, x1 equal to 0.25, x2 equal to 0.26, and x3 equal to 0.27. Now substituting this value in above equation, we can calculate df by dx at 0.27. Now here we have to calculate df by dx at x3, which is equal to 0.27. Hence we will substitute x with 0.27 and put above given values in the equation, and hence we get df by dx at 0.27 equal to 0.9550. Now for d square f upon dx square at x1, we will double differentiate equation 1. After differentiating once equation 1, we will get this first equation, and on again differentiating equation 1, we will get d square f upon dx square equal to delta square f forward difference operator square f1 upon 2 into h square 1 minus 0 plus 1 minus 0 means 2. Here del square f1 equal to minus 0.0001, h equals to 0.01. This value we have taken from difference table, and substituting these values in above equation, we will get d square f upon dx square at x1 equal to minus 1. Now the second question is based upon Simpson's rule. The question is integrate the function tabulated below using Simpson's rule. We have some values of x and corresponding value of fx. So we have to integrate the function using Simpson's rule. But we can observe here that we have 10 points, but Simpson's rule require an odd number of points. Therefore, we will use trapezoidal rule for the first 2 points and Simpson's rules for the rest trapezoidal rule. Trapezoidal rule is given by integrating f of x from x to x plus nh equal to h by 2 sum of y0 plus yn plus twice of y1 plus y2 plus yn minus 1. Here y0 equal to 4 and y1 equal to 2 from the table. Integrating f of x from minus 0.6 to minus 0.5 equal to h by 2 y0 plus y1. Here h equal to class interval, which is 0.1. y0 is 4 and y1 is 2, hence y0 plus y1 is 6. Now integrating f of x using Simpson's 1/3 rule. Simpson's one-third rule states that integration of f of x from x to x plus nh equal to h by 3 y0 plus yn plus 4 times of y1 plus y3 plus that is yn minus 1 plus twice of y2 plus y4 to yn minus 2. Here y0 equal to 2, y1 equal to 3, y2 equal to 8, y3 equal to 4, y4 equal to minus 2, y5 equal to 2, y6 equal to 3, y7 equal to 5 and y8 equal to 8. Now substituting above values in the formula, we will get this equation, and Simpson's one-third rule equates to this. Now combining both rules, we will get integration of f of x from minus 0.6 to 0.3 equal to integration of f of x from minus 0.6 to minus 0.5 plus integration of f of x from minus 0.5 to 0.3 with respect to dx. Now substituting the values of integration from previous slides, we can have integration of f of x minus 0.6 to minus 0.3 equal to 3.1. Hence the answer is 3.1. Our question 3 is based on forward difference operators and backward difference operator. The question is, the population of a city in census taken once in 10 years is given below. Estimate the population in the year 1925, 1975 and 1985. The difference table we can form is this. Here we have again calculated delta f, delta square f and delta cube f. Here delta f is the forward difference operator. Now we can see that delta cube f is nearly 0. We can fit a quadratic and use only up to second differences. Now we can see 1925 is near the top of the table, means near to 1921. So we use the forward difference formula. The forward difference formula can be given by f of a plus hu equal to f of a plus u into delta f of a plus u into u minus 1 upon factorial 2 into delta square f of a. We know that f of a plus hu equal to e to the power u. E is shift operator and f of a. Now u can be calculated as a plus hu equal to 1925. 1925 is the year for which we have to calculate population. Here a equal to 1921 and h is the class interval which is 10. So we have u equal to 0.4. From difference table, f of a equal to 35, delta f of a equal to 7, del square f of a equal to 9. Substituting this value is in forward difference formula, we will get 37 as the population in the year 1925. Now calculating population for the year 1975. 1975 is near the bottom of the table, means near to 1981. Hence we use backward difference formula. Backward difference formula can be given by f of a plus nh plus us equal to f of a plus nh plus u into backward difference operator into f of a plus nh plus u into u plus 1 upon factorial 2 into backward difference operator square f of a plus nh. Here f of a plus nh plus u is equal to e to the power u. E is again shift operator into f of a plus nh. Here we can calculate u by using a plus nh plus us equal to 1975. 1975 is again the year at which we have to calculate the population. Here a plus nh equal to 1981. A plus nh equal to 1981 because it is the last value of x or year. Now u equal to minus 0.6. The difference table, from the difference table we have got f of a plus nh equal to 220, backward difference operator f of a plus nh equal to 55, backward difference operator square f of a plus nh equal to 10. Substituting this value in backward difference formula which is defined above, we will get 186 as the population in the year 1975. Now 1924 is outside the values of the table because 1981 is the last value of the table. Thus we can't interpolate. If we assume the trend outside the table is same as inside, then we can use same polynomial. Now by backward difference formula, as we have seen earlier, we can calculate u equal to 0.3. From difference table, we have f of a plus ns equal to 220, backward difference operator f of a plus ns equal to 55, backward difference operator square f of a plus ns equal to 10. Substituting this value in backward difference formula, we will get 23, 238. 238 is the population in 1984. Now the question 4 is based on Gauss-Seidal method for calculating the values of variables. Here the variables are x1, x2 and x3. The question is solve the following set of equations by Gauss-Seidal method, and these three equations are given. Is row interchange necessary for the above equation? This is our question number 4. First of all, we will calculate the relative error for Gauss-Seidal method. Relative error is calculated to detect whether we are converging towards the correct answer or diverging from the correct answer. If the relative error is less than 1, we assume that we are converging towards the correct answer. But if relative error is greater than 1, we are diverging from the correct answers. Here relative error is given by a12 into a13 into a21 into a23 into a31 into a32 upon a11 into a22 into a33. Conclusively, product of non-diagonal element upon product of diagonal element. This is our relative error for Gauss-Seidal method. Here a11 equal to 2, a12 equal to 4, a13 equal to 2, a21 equal to 2, a22 equal to 1, a23 equal to 2, a31 equal to 4, a32 equal to 1, and a33 equal to minus 2. Therefore, relative error can be calculated as 32, which is greater than 1. Hence, using the same sequence of equations given in the question, the relative error is greater than 1. It means we are diverging from the correct answer. So let's check relative error after performing row interchange so that the diagonal element can highest value in that row. So the order of row will be 4x1 means last row is set as first row is set as second row, and middle row is set as last row. Here a11 values of all these constant coefficients will be changed, and this is equal to this. Therefore, relative error will be equal to minus 1 by 2, which is less than 1. It means after interchanging the rows, we are converging towards the correct answer. Therefore, we will follow this sequence of equation. The sequence of the equations are 4x1 plus x2 minus 2x3 equal to 0. This is our first equation. 2x1 plus 4x2 plus 2x3 equal to 15. This is our second equation. And 2x1 plus x2 plus 2x3 equal to minus 5 is our third equation. In the Gauss-Seidal method, initially x10 to x30 are set to 0 and x11 is calculated from equation 1. It means x1 and x3 x2 and x3 are taken as 0, and we can calculate x11 from equation 1. Here x11 equal to 0. Then this value of x11 is substituted in equation 2, and 0 value of x3 is substituted in equation 2 to calculate value of x21. means value of x2 for first iteration. Here x11 equal to 0 and x30 equal to 0. So x21 equal to 15 by 4 means 3.75. Now putting the values of x11 and x21 in the equation 3, we will get value of x31. X11 is 0 and x21 is 15 by 4. Now x31 equal to minus 35 by 8 or minus 4.375. Now for iteration 2, these values of x21 and x31 are used to calculate value of x12, means value of x1 for second iteration from equation 1. And these values of x12 means value of x1 for second iteration and value of x3 for first equation are used to calculate value of x2 for second iteration from equation 2. Then x32 is calculated by putting the value of x12 and x22. Means we can calculate value of x3 for second equation by for second iteration by putting the value of x1 for second iteration and x2 for second iteration in equation number 3. And so on we can continue to iterate till two iterations have nearly the same values for x1, x2 and x3. The values of x1, x2 and x3 for all iterations are tabulated as follow. We have done 9 iterations and we can see at iteration number 8 and iteration number 9 the value of x1, x2 and x3 are nearly same. The difference is only 0.01. So the value of x1, x2, x3 at iteration f9 are the required values of x1, x2 and x3 from the three given equations. Hence x1, x2, x3, x1 equal to minus 3.05, x2 equal to 6.77 and x3 equal to minus 2.77. This will end the solution for fourth question. Thank you for watching this video.